projects. In this video, we are going to explain about the project titled Water Quality Prediction Using Machine Learning. Introduction. The quality of water directly affects various aspects of life and the environment. For humans, access to clean and safe drinking water is essential for maintaining health and well-being. Poor water quality can lead to waterborne diseases and other health issues. Additionally, water quality is vital for sustaining ecosystems, including aquatic habitats and biodiversity. Economic activities such as agriculture, tourism, and industry also rely heavily on adequate water quality for productivity and sustainability. Traditional methods of assessing water quality often involve collecting water samples and conducting laboratory analysis, which can be time consuming and resource intensive. These methods may not provide real time data or comprehensive spatial coverage, limiting their effectiveness for timely decision making. Additionally, the costs associated with laboratory analysis and field sampling can be prohibitive, especially for large scale monitoring efforts. In response to the limitations of traditional methods, this project seeks to utilize machine learning techniques to predict water quality. Machine learning algorithms can analyze large data sets quickly and identify complex patterns that may not be apparent through traditional statistical approaches. By leveraging machine learning, we aim to develop predictive models that can provide real time and accurate forecasts of key water quality indicators. The project utilizes environmental data to forecast water quality based on key indicators like pH, dissolved oxygen, and turbidity. This predictive model aids decision making in water resource management and pollution control. Objective of the project aims to utilize machine learning techniques to develop models that can accurately forecast key water quality parameters. By doing so, it seeks to improve the efficiency and effectiveness of water quality assessment and monitoring processes. Various machine learning algorithms such as logistic regression, decision tree, support vector machine, and more are employed in the project to predict water quality. These algorithms analyze data patterns to make predictions about water quality indicators. The project employs water quality indicators such as pH levels, dissolved oxygen turbidity, and nutrient levels as input variables to predict whether the overall water quality is classified as good or bad. By analyzing these indicators, the project aims to assess water quality and provide insights into its sustainability for different purposes. Algorithm performance is compared using metrics like accuracy, precision, recall, and FN score to identify the most reliable prediction model. By improving water quality prediction, the project aids stakeholders and the public in making informed decisions related to resource management, pollution control, and public health interventions. This contributes to the preservation of water resources and fosters sustainability. Software and hardware requirements. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Software requirements of the project are application is Anaconda, primary language is Python, front-end framework is Flask, back-end framework is Jupyter Notebook, database is SQLite 3, front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing libraries. This module involves importing essential libraries such as Pandas for data manipulation, NumPy for numerical operations, Matplotlib and Seaborn for data visualization, and scikit-learn for machine learning algorithms. Importing dataset. The dataset containing historical water quality data is imported into the programming environment. This dataset serves as the foundation for model training and prediction. Exploratory data analysis. In this module, the dataset is explored to gain insights into its structure and characteristics. Descriptive statistics such as mean, median, and standard deviation are calculated. Data summaries, histograms, and box plots are used to visualize the distribution of variables. EDA helps in identifying patterns, trends, and potential issues such as missing values or outliers. Data visualization. This module focuses on creating visual representations of the data to enhance understanding. Scatter plots, line charts, and heat maps are used to visualize relationships between variables. Data visualization aids in identifying correlations, patterns, and anomalies within the dataset. Feature selection. Feature selection involves identifying the most relevant variables that contribute significantly to the prediction task. Techniques such as correlation analysis, feature importance ranking, and dimensionality reduction methods like PCA, principal component analysis, can be employed. Selecting informative features helps improve model performance and reduces computational complexity. Training and building the model. In this module, machine learning models are trained using the selected features and target variables. The dataset is divided into training and testing sets to assess model performance. Various algorithms such as logistic regression, decision trees, support vector machines, and more are trained and evaluated. Performance comparison. Model performance is evaluated using appropriate evaluation metrics such as accuracy, precision, recall, and FN score. Cross validation technique is used to ensure robustness and generalization of results. Performance comparison helps identify the best performing model for water quality prediction. Flask framework with SQLite for sign up and sign in. This module integrates the Flask web framework with the SQLite database to implement user authentication functionalities such as sign up and sign in. Flask provides tools for building web applications, while SQLite is used as a lightweight relational database management system. Users can securely create accounts, log in, and access the prediction system. User gives input. Users input relevant information or parameters related to water quality through the front-end interface. Input fields include parameters such as temperature, pH levels, dissolved oxygen, etc. The given input is pre-processed for prediction. User input is pre-processed to ensure it is in the appropriate format and compatible with the trained model. Pre-processing steps include scaling, encoding categorical variables, or handling missing values. Trained model is used for prediction. The pre-processed user input is passed to the trained machine learning model to make predictions about water quality. The model utilizes the input features to generate predictions regarding the quality of water, as good or bad. Final outcome is displayed through front end. The predicted outcome indicating the quality of water based on the user input is displayed through the front end interface. Users can visualize the predicted result and make informed decisions based on the water quality predictions provided by the system. Algorithms used to implement this project, we have utilized the following algorithms. The first algorithm is DB-scan clustering. DB-scan, density-based spatial clustering of applications with noise, is a clustering algorithm that groups together points that are closely packed together based on density. It works by identifying core points which have a specified number of neighboring points within a given radius and expanding clusters from these core points. DB-scan is particularly useful for identifying clusters of arbitrary shapes and handling noise or outliers effectively. DB-scan is utilized to identify clusters of similar water quality samples based on their feature values, helping in targeted monitoring or intervention efforts in areas with similar water quality characteristics. Coming to the next algorithm, which is logistic regression. Logistic regression is a statistical method used for binary classification tasks, where the output variable, dependent variable, is categorical and has only two possible outcomes. It estimates the probability that a given input belongs to a particular class using a logistic function, which maps the input features to probabilities between 0 and 1. Logistic regression models the relationship between the input variables and the probability of the binary outcome using a linear function. Logistic regression is applied to predict whether water quality is classified as good or bad based on input features such as pH levels, dissolved oxygen, etc. Decision tree. Decision tree is a tree-like model consisting of nodes representing features, branches representing decisions, and leaves representing class labels. It makes decisions based on splitting the dataset into subsets based on the value of input features with each split maximizing the homogeneity of the resulting subsets. Decision trees are interpretable and can handle both numerical and categorical data. Decision tree is used for water quality prediction by splitting the dataset based on features such as pH, temperature, etc., and making decisions about water quality classifications at each node. Coming to the next algorithm, which is support vector machine. SVM is a supervised learning algorithm used for classification and regression tasks. It finds the hyperplane that best separates data points of different classes by maximizing the margin between the classes. SVM can handle high dimensional data and is effective in dealing with non-linear relationships between features and labels. SVM is applied to classify water quality as good or bad based on input features. It can handle complex relationships between features and labels and is suitable for binary classification tasks. Bagging classifier. Bagging, bootstrap aggregating is an ensemble method that builds multiple base classifiers using bootstrap samples of the training data and aggregates the predictions. It reduces variance and overfitting by averaging predictions from multiple models trained on different subsets of the data. Bagging works well with unstable models and can improve the robustness and stability of predictions. Bagging classifier is used to combine predictions from multiple base classifiers trained on different subsets of the water quality data, improving the overall predictive performance of the model. Coming to the next algorithm, which is AdaBoost. AdaBoost, adaptive boosting, is an ensemble method that combines multiple weak learners to create a strong classifier. It trains a series of weak learners sequentially, with each learner focusing on the instances that were misclassified by the previous ones. AdaBoost assigns weights to each instance in the dataset, and subsequent weak learners focus more on the misclassified instances. AdaBoost is applied to enhance the predictive performance of water quality models by sequentially training weak classifiers on repeatedly modified versions of the data, focusing on misclassified instances and improving overall accuracy. Voting classifier. Voting classifier combines the predictions of multiple individual models and predicts the class with the most votes. It is used with different types of base classifiers and different voting strategies, such as hard voting, simple majority, or soft voting, weighted average of predicted probabilities. Voting classifier can improve prediction accuracy by leveraging the strengths of different individual classifiers. Voting classifier is used to aggregate predictions from different models to make a final prediction about water quality based on consensus voting, leading to more robust and accurate prediction. Coming to the next algorithm, which is KNN, K nearest neighbor. KNN is a non-parametric lazy learning algorithm used for classification and regression tasks. It predicts the class label of sample by comparing it with the k nearest neighbors in the training set, where k is user defined parameter. KNN is simple to implement and can handle complex decision boundaries. KNN is applied to predict water quality based on the similarity of input features to those of neighboring samples in the training dataset, making it suitable for data with nonlinear relationships. XGBoost, extreme gradient boosting, is a scalable and efficient implementation of gradient boosting algorithms. It builds a series of decision trees sequentially, with each tree correcting the errors of the previous ones. XGBoost incorporates regularization techniques to prevent overfitting and can handle missing values and sparse data. XGBoost is used to improve the predictive accuracy of water quality models by iteratively refining the model's predictions to achieve higher accuracy and better generalization. Coming to the next algorithm, which is gradient boosting. Gradient boosting is a machine learning technique for regression and classification tasks, where weak learners are added sequentially to correct errors made by the previous models. It works by fitting a series of weak learners to the residuals of the previous models, gradually reducing the error in the prediction. Gradient boosting can handle both regression and classification problems and is robust to outliers. Gradient boosting is employed to build an ensemble of models for water quality prediction iteratively refining the model's predictions to achieve higher accuracy and better generalization. Coming to the next algorithm, which is random forest. Random forest is an ensemble learning method that builds multiple decision trees during training and outputs the mode of the classes as the prediction. It introduces randomness by using bootstrap sampling and random feature selection, which helps reduce overfitting and increase model diversity. Random forest is robust to noise and outliers and can handle high dimensional data. Random forest is used to predict water quality based on the majority vote of multiple decision trees trained on different subsets of the data, improving robustness and accuracy of the predictions. Comparison graphs. Comparison graphs offer a visual breakdown of how our models perform across essential evaluation metrics. Models are compared with the evaluation metrics accuracy, precision, recall, and FN score. This is the accuracy comparison graph. Here on the x-axis we have algorithm name and on the y-axis we have accuracy score. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positives and true negatives, to the total number of instances. This is recall comparison graph. Here on the x-axis we have algorithm name and on the y-axis we have recall score. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is precision comparison graph. Here on the x-axis we have algorithm name and on the y-axis we have precision score. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions, true positives plus false positives. This is FN comparison graph. Here on the x-axis we have algorithm name and on the y-axis we have FN score. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. The algorithm which is performing best in all the evaluation metrics will be used for prediction. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model file, which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command is used to change the current directory to the code folder's path. Compile the app.py file using the command python space app.py. Here I'm typing python space app.py and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser, I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. If we are new users, we need to register first. So click on sign up button here. Here we need to enter all these details to register, but I have already registered. So click on sign in. Here we need to enter the username and the password which we have registered and then click on sign in button. We have signed in successfully and we are redirected to the production page. Here we need to enter all these parameters. Before entering the parameters, let us understand the parameters. So the first one is temperature. Measurement of the water's warmth, which influences chemical reactions, biological processes, and the solubility of gases like oxygen. DO, which is dissolved oxygen, indicates the amount of oxygen dissolved in water, crucial for the survival of aquatic organisms and indicative of water quality. pH measures the acidity or alkalinity of water on a scale from 0 to 14, affecting chemical reactions, nutrient availability, and the health of aquatic life. Conductivity reflects the water's ability to conduct electrical currents due to the presence of dissolved ions, providing insights into the concentration of salts and other dissolved substances. BOD, which is biochemical oxygen demand, measures the amount of oxygen consumed by microorganisms while decomposing organic matter in water, indicating the level of organic pollution and the health of aquatic ecosystems. Nitrate ON plus nitrite ON represents the combined levels of nitrate and nitrite nitrogen compounds in water, which can originate from agricultural runoff, wastewater, and other sources and can lead to eutrophication and contamination. Fecal coliform indicates the presence of fecal bacteria in water, primarily originating from the intestines of warm-blooded animals, serving as indicators of fecal contamination and the potential presence of waterborne pathogens. Total coliform represents the total count of coliform bacteria in water, including both fecal and non-fecal types, used as indicators of water quality and contamination. So here, we need to enter these parameters, and after entering the parameters, the application will predict the water quality. So I'm entering the parameters now. So here I have entered all the parameters. Now click on submit button. So here we can see we got the result, bad quality of water. Let us enter another set of parameters and check the quality of water. So here I'm entering another set of parameters now. So here I have entered another set of parameters. Now click on submit button. So here we can see we got the result, good quality of water. In this way, just by entering the parameters, we can predict the quality of water as good or bad. Let us enter another set of parameters. So here I'm entering another set of parameters now. So here I have entered another set of parameters. Now click on submit button. So here we can see the result, bad quality of water. We can predict the quality of water by entering those parameters. Now click on sign out link here. The conclusion of the project is the project achieved the successful development of predictive models using machine learning techniques to assess water quality. This indicates progress in leveraging advanced technology for improving environmental monitoring and management practices. By implementing various algorithms and data pre-processing methods, the project demonstrated the effectiveness of machine learning in enhancing prediction efficiency and accuracy. This highlights the potential of machine learning to handle complex data sets and extract valuable insights for water quality assessment. The conclusion of the project hold promising implications for environmental agencies, water resource administrators, and policymakers. They provide valuable insights that can facilitate more informed decision-making processes, ultimately leading to better management of water resources and environmental preservation efforts. Future research directions involve refining the existing predictive model by exploring additional machine learning algorithms and integrating new data sources. This continuous improvement process aims to enhance prediction accuracy and address evolving challenges in water quality assessment, contributing to ongoing advancements in environmental science and technology.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.